Complex systems usually descend into chaos, but some mathematical systems possess an architecture so rigid they experience an abrupt, perfectly predictable mathematical collapse. We can observe this behavior within a specific mathematical environment, an operator, labeled L, acting across a two-dimensional integer lattice, known as z². This diagram illustrates the theorem's final output. The norm of a function f decays by half with every iteration, k, producing the equation L to the k f equals O of 1 over 2 to the k. Dynamically, this strict geometric contraction mathematically erases exactly 50% of the amplitude with every step forward. In standard linear algebra, calculating a decay rate for a finite closed matrix is a solved foundational problem. But our operator L is a genuine infinite-dimensional operator. In this unbounded space, standard finite eigenvalue theorems completely fail. To understand how this strict decay survives infinity, we will reverse engineer the theorem. We will work backward from this guaranteed 1/2 decay rate to uncover the structural machinery preventing infinity from breaking the math. The survival of this exact bound relies on three specific interventions: a mean zero restriction, a property called quasi-compactness, and a uniform block structure. Let's examine the very first premise of the theorem, the specific space the operator acts upon. The theorem restricts its inputs to a functional space labeled H0 alpha. These functions operate on the z² lattice and strictly possess a mean of 0. This restriction is required because in Markov or transfer operators, there is inherently a dominant trivial eigenvalue of exactly 1. This 2D complex plane plots eigenvalues. The large circle has a radius of 1, with a distinct point plotted exactly at lambda equals 1. This steady-state eigenvalue prevents decay and dominates the space. By restricting to mean zero functions, we systematically eliminate this trivial eigenvalue. With that dominant eigenvalue gone, the system's long-term behavior falls entirely to the next largest spectral feature. For this operator, the theorem proves that the next largest eigenvalues sit perfectly at a new spectral radius of exactly 1/2. Restricting the domain to mean zero functions drops the operator's speed limit from 1 to exactly 1/2. It'd be convenient to declare the spectral radius as 1/2 and consider the problem solved, but we still have an infinite dimensional space to contend with. In finite systems, a spectral radius is a straightforward outer boundary drawn around distinct isolated points. Infinite dimensions, however, are far more chaotic. When these mathematical operators scale to infinity, they develop what is known as an essential spectrum. The essential spectrum is a continuous band or cloud of eigenvalues. Unlike well-behaved discrete points, this cloud can schist and expand. This split screen visualizes the threat. Left, the finite system holds sharp, isolated points. Right, the infinite system's dots blur into a continuous essential spectrum, bleeding toward our 1/2 boundary line. If this cloudy spectrum touches the 1/2 radius, the precise geometric decay rate is destroyed. The theorem relies on a specific property to prevent this bleed: quasi-compactness. Quasi-compactness guarantees the essential spectrum is fiercely compressed into a radius strictly smaller than the overall spectral radius. This ensures the cloudy spectrum is squeezed deep into the center, leaving only isolated sharp dots at the 1/2 boundary. Because of this compression, any eigenvalues touching the 1/2 boundary are guaranteed to be isolated and predictable, not a continuous mass. Faster, more urgent tone. That strict isolation is what makes the 1/2 bound mathematically reliable. Quasi-compactness prevents the continuous spectrum from blurring or breaking the strict 1/2 decay barrier. This brings us to a final structural question. How do mathematicians actually compute and verify this quasi-compactness for an operator that is infinitely large? They use truncation, cutting the infinite matrix down to a finite calculable level denoted as n. This introduces the truncation trap. It's a massive error to assume that a bound proven for a finite n by n matrix automatically holds true as n approaches infinity. This animation shows the vastness of the true infinite operator. The highlighted square section in the corner represents our truncation level, n. Without internal safeguards, as you expand n toward infinity, the mathematical norms, the energy of the matrix components, could wildly inflate and blow up. To counter this, the theorem introduces its final structural safeguard, the uniform in n block structure. Uniform in n dictates that no matter how infinitely large the matrix grows, the bounds on its internal building blocks remain perfectly rigid and constant. This rigid uniformity is the mechanism that connects finite approximations to infinite reality. Because the bounds never warp as the structure scales, the finite truncation behaves identically to the genuine infinite-dimensional operator. The uniform block structure provides rigorous justification for the 1/2 spectral radius to persist as the model scales from finite to infinite space. We can now view the entire reverse-engineered mechanism working in unison. First, the uniform block structure provides the stability, allowing us to safely push our matrix calculations toward the infinite limit. Second, once at infinity, quasi-compactness activates, compressing the chaotic essential spectrum deep inside the core. Third, by strictly analyzing mean-zero functions, we bypass the dominant steady-state eigenvalue entirely. This diagram illustrates these 3 layers combining to strand the maximum spectral radius at exactly 1/2. So what happens when our function f actually passes through this highly restricted operator L? Because the mathematical speed limit is absolutely capped at 1/2, every single iterative application acts as a literal physical halving of the function's magnitude. For any mean-zero function f, applying the genuine infinite-dimensional operator L a total of k times algebraically guarantees a strict, unyielding geometric decay bounded by O of 1/2 to the k.